be right back. You need something to learn. Let's pray, and we'll start. Father, thank you for today. Thank you for all that you're doing in our lives all the time. Thank you for the wonderful world that you've made and how you've made everything and how it's good, and you've made it for your glory and for our good by your tremendous grace. As we study today about Hess's law, and just the energy that's involved in everything that is, and all these chemical reactions, Lord, it's just amazing to think about how all things were made by the power of your word. You spoke the world into existence, and you uphold the world by the power of your might and the power of your word. And you are so good. Help us as we study these things. Help our minds to be clear, and to put them in a good order, and to retain them. Help me as I teach, Father, to just be clear and concise and helpful. We pray this in Jesus' name. Amen. All right. Well, as I was telling the gentleman earlier, today will probably be a little bit short. We're going to finish this chapter, and I'm not going to start the next one. I owe you guys some homework. I've probably been saying that a little while. Hopefully I'm to the point that I can actually get that done. I'm going to try to focus the homework down to problems that mirror what will be on the test, just so you can be super focused. You're not having to do more than you have to do. So basically, if you can do it, you can do it. You don't have to, go crazy. I will do what I did on the last test, where I take the problems that I give you and I just tweak numbers, and, to where it's literally very comfortable for you. Okay, you guys did well on that, and we'll do well on this one. Remember, show all work on everything. That becomes important today, because we're going to have like some sign stuff where it's, you got it, like the inverse of an inverse. Well, that's a positive, right? Or not an inverse, like you're going to subtract a negative. That becomes, and sometimes you're going to like subtract a negative from a negative that was, you got to keep track of it all, show everything, okay? Well, that said, we need to pick up where we left off, if we can find that. I'm not sure where that was. Here we go. We didn't do anything with combustion. What's the last problem you guys have? Oh my goodness, what are you doing?
I think it was the acetylene combustion or something.
Okay. Well, I gotta find that room. Acetylene? Yeah. Okay, good. So let's just do, this one's not hard, let's do this one as a review. Okay, so warm up. How much heat is produced by the combustion of 125 grams of acetylene? So we're looking for delta H of 125 grams of acetylene, right? So we're given this 125 grams, so we'll go 125 grams of acetylene. And then what we need to do is just figure out the number of moles that is, right? So we're going to go 1 mole, and we'll come up with the molar mass. And then I need to figure out how many joules per mole this thing releases, right? So when I do this, I do know this. I know that this number is 1,301.1. It's negative. It's exothermic. Joules per 1 mole of C2H2. Okay. And then the question is, what's my formula weight for C2H2, which is acetylene, right? So it's 12 times 2 is 24, plus 2 is 26. So 26 grams per mole. I say that because the formula is C2H2. Okay, so that's pretty easy to do. So I have 25 grams times 1 mole over the molar mass times the number of joules released per mole, or per mole, apparently. What I was doing there. And when I run that math, and you guys have calculators, right? So run that math. What do you get?
This is supposed to be a fairly big
Yeah.
number. Okay, I got negative 6,255.28. Is that right?
Yeah, you get 6.25 times 10 to the third kilojoules.
It's negative.
Yeah. Yeah, so it's interesting, the way they wrote this, how much heat is produced. We know that sign tells us that we are producing heat. Okay, so that's great. Well, now we're going to look at a new concept. It's enthalpy of formation. So this is how much energy was released. So next one's going to be, what does it take to make something? All right, things you need to know. Standard enthalpy of formation is an enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from free elements in their most stable states under standard state conditions. These values are especially useful for computing or predicting enthalpy changes or chemical reactions that are impractical or very dangerous to carry out, or for processes for which it is difficult to make measurements. If we have values for the appropriate standard enthalpies of formation, we can determine the enthalpy change for any reaction, which we will practice in the next section on Hess's law. So here's the example they're giving. The standard enthalpy of formation of CO2 gas is, this is delta H of formation of CO2 gas, is negative 395.5 kilojoules per mole. Okay. It's an exothermic reaction. The question that we're asked, so this is the amount of energy that it takes to make this, or that is released when we make this, okay? Now, it's saying we can break this down into constituent parts to make this. So we take carbon, which is solid. Solid carbon, you might think of diamonds. For our purposes, you need to think of graphite, okay? So graphite plus oxygen, so a combustion reaction, right? It's going to be a gas. Will yield CO2 gas. Okay. And this combustion reaction releases negative 395.5 kilojoules per mole. It says they're starting with the reactants at a pressure of 1 atmosphere and 25 degrees centigrade. And ending with 1 mole of CO2, also at 1 atmosphere and 25 degrees centigrade. For nitrogen dioxide, so that's NO2. That's going to be our product, NO2. This is another formula here. We want to have N2 plus O2. This is a gas, right? This is a gas. What do I need to do to balance this?
2 on the other side.
Nope, because I want exactly 1 mole of this. So this is one of the things with these types of reactions. my goal is exactly 1 mole of my product, so I'm going to have to do something funky on the other side.
Half.
I'm going to put a half, right? I need 1/2 of this nitrogen plus all this oxygen will give me NO2, okay? And the delta H of this one is 33.2 kilojoules. Okay. All right. We're going to do something with this, okay? It says ozone, O3, forms from oxygen by an endothermic process. Ultraviolet radiation is the source of energy that drives us. So basically what happens is up in our atmosphere, UV light that enters the atmosphere interacts with the oxygen, and it causes the oxygen to, gives enough energy to break the bonds, but then they want to reform immediately. Sometimes they reform back into oxygen, sometimes they reform into ozone, O3. And so what we have here is this. It takes 3 O2s to yield 2 O3s. Okay? And it says here that the enthalpy of formation for this is 286 kilojoules of energy. All right? Is that really all it wants? No, okay. It wants us to calculate the amount of energy for 1 mole and write the formula. So given this information, we want to rewrite this formula in its entirety, both what this looks like and what our enthalpy of formation looks like, okay? Remember, I always want 1 mole of my product. So what do I need to do?
Divide by 2.
Divide everything by 2, which means this will come out to be 3/2 O2 to yield 1 O3. And what do I need to do here?
Divide by 2.
Cut that in half, so my delta H equals 143 kilojoules. Okay? So nothing hard about that. That one's pretty straightforward. Let's do another one that's very, very similar. Let's do hydrogen gas. It says hydrogen gas reacts explosively with gaseous chlorine, Cl2, to form hydrogen chloride. What is the enthalpy change for the reaction of 1 mole of H2 with 1 mole of Cl2 if both the reactants and the products are at standard conditions? The standard enthalpy of formation of HCl is negative 92.3 kilojoules per mole. I gotta erase this a little bit. Information yet. I have H2 plus Cl2, and I'm going to get HCl. I need to balance this. What is it? 2. Okay. What is the enthalpy change for the reaction 1 mole of HCl with 1 mole of Cl2 if both the reactants and the products are at standard conditions? The standard enthalpy of formation of HCl is, so delta H for HCl is negative 92.3 kilojoules per mole. Okay. So what does this information tell me?
You need that much energy to form 1 mole?
Form 1 mole, right? Now my question is, what is the enthalpy change for this reaction? So over here, I want to know, hey, what's the enthalpy for the formation of 1 mole of this? In this case, I have the information for 1 mole, but that's not what it's asking. It wants to know what the enthalpy change for this reaction is. So what do I need to do? Multiply by 2. So I've got 1 mole of HCl right over negative 92.3 kilojoules, right, times 2 moles of HCl, and obviously you can tell that I have inverted this and I need to flip it. So I want kilojoules, I don't want per kilojoule. So I'm going to go negative 92.3 kilojoules over 1 mole HCl times 2 moles of HCl. And when I do it this way, I will get something 0.6. What do I get? Like 184.6 kilojoules? And that's right. Okay. Good. All right. Let's do the next one. Actually, this might just seem boring and tedious, but I greatly appreciate how they're doing this stepwise building. If we just dove straight into Hess's law, we'd be getting killed right now. All right. Here we go. Write the heat of formation reaction for the following. So our task is to, you guys need to actually write this out, okay? Okay, we're going to do 2 of them. The first one is for the production of C2H5OH as a liquid. Okay? So what we want to do with this is we want to make this, our rule that we said earlier, we haven't really touched it yet, says that you want to use the heat of formations of the constituent elements in their lowest energy state. So what are my constituent elements here? Give me 1 second. Sorry, give me 1 second. Well, this is okay. So what are my constituent elements? What states will I find?
Right.
Huh?
CH4.
Okay, so I've got carbon, right? Carbon. What's my lowest energy state for carbon? It's going to be graphite. Okay. So it's going to be solid carbon as graphite. Okay. And next is hydrogen. And how will I find hydrogen? It's a gas, right? So it's H2. Okay. And the other one? Oxygen. Yeah, that's O2. Make sure I haven't led you astray on any of this. Yeah. Okay. So we got these things, and they need to yield for us C2H5OH, which means we're going to have to do some stuff, right? So let's think about carbon. What do I need to do with carbon?
Multiply by 2.
Multiply by 2. What do I need to do with hydrogen? How many hydrogens do I have here? 6, right? 5 plus 1 is 6. So what do I need to do over here? 3. Good. Okay. And oxygen? Half. Good. Okay. All right. What does it want you to do with that? Well, that's it. It doesn't even want you to do anything with the delta H. Okay, good. That's it for that one. Again, we're building stepwise. We're going to use these things coming up. Okay, let's do the next one. The next one is it's for calcium diphosphate. So Ca3 PO4 2 solid, right? So what are my constituent elements here? Calcium plus phosphorus plus oxygen is going to yield Ca3 PO4 2 solid. Now, something you need to know here about phosphorus is that it exists tetratomically. I think I just made that word up, but it's P4. It's got to be a word. Diatomically, tetratomically, it's got to be a thing. All right. You quote me on that. Okay. So, how many calciums do I need? 3. How many phosphoruses do I need? Well, I need 2, and then the exist here is 4, so I need half of that. Good.
Why is there a 4 by the B?
This is how it exists. You will not, like oxygen in the atmosphere, or oxygen anywhere, you'll never find oxygen just oxygen, because it always wants to make 2 bonds, right? So the lowest energy state that exists naturally for oxygen is O2. Phosphorus does not exist as just P, or as P2, or as P3. The lowest energy state that you'll find it in is P4.
Okay. So why is it not 2 by the O then?
Help me out.
Well, if there's oxygen.
Oh, I haven't got to the oxygen yet.
Oh,
That's where I'm going next.
oh, okay.
Okay, good question. So what should there be in front of this? This should be O2. Oh, I got you. I'm sorry, because I forgot to write it.
Yeah.
Or I was in the midst of writing. I don't know. Who knows? I get distracted. So, good question. How many oxygens do I need?
8.
I need 8 total. Exists in 2, so I need 4. Right? And that should be the correct answer. That's the correct answer. Good. Okay. No problem. Let's do another one. All right. Write the combustion reactions for heated combustion reactions for 2 of them. Number 1 we're going to do is C2H5O C2, oh, I need glasses, 2H5. Okay. All right, so how do I make this? What are my elements? Carbon, hydrogen, and oxygen. Okay, so how many carbons do I need? 4. I need 4. How many hydrogens? 10 exist in this 2, so I need 5. How many oxygens? 1. I have 2, so this has to be a half. Right? That's good. That's the correct answer. Let's do this last one before we dive into Hess's law stuff. So in Na2CO3, sodium carbonate. Okay, so I need Na, and I need carbon, and I need oxygen, and that's going to result in sodium carbonate. Okay. How many sodiums? 2. How many carbons? 1. How many oxygens? 3. I need 3. What'll I put here then?
Yes.
3 halves. Okay. That's it. There are 2 ways to determine the amount of heat involved in a chemical change. You can measure it experimentally, or you can calculate it from other experimentally determined enthalpy changes. In other words, if I know the amount of energy it takes to make this, and to make this, and to make this, then I know the amount of energy it takes to make this. Okay. So we're going to do some work with that principle. This is Hess's law. Okay. This type of calculation usually involves the use of Hess's law, which states that if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. Let me write that out. This is worth knowing, okay? If a process or a reaction can be written as the sum of several stepwise processes, then, so we have an if, we have a then the enthalpy change the total process equals the sum of the enthalpy changes of the various steps. So I want to consider the reaction of carbon and oxygen to make CO2. Well, when this happens, it actually happens in 2 steps. The first step is carbon combines with half of an oxygen to produce carbon monoxide. The second step is that carbon monoxide combines with half of an oxygen to produce carbon dioxide. The summation of these 2 things gives me carbon, or excuse me, the carbon monoxides would cancel out, right? The half of the oxygens would add up, and the carbon would remain. Let me say that again. because these two are on opposite sides of the sign, they will cancel out. Okay? Everything else remains, and when I sum this out, I get carbon solid, plus, add these two together, I get a whole O2, will yield CO2. So if I know the amount of energy involved in this reaction and the amount of energy involved in this reaction, I can sum them together according to Hess's law, because these are two steps in the formation of CO2, and I can sum them up and it will equal the sum of the various steps. So when I think about that, I need to know that step 1 releases negative 111 kilojoules, and that step 2 releases 283 kilojoules, right? And therefore, delta H for the entire equation is how much?
394.
Yeah, 394. Fairly straightforward. So far, so good. Let me erase some stuff and we'll dig in. All right. Let's do another example. Delta H is directly proportional to the quantities of reactants or products. For example, the enthalpy change for the reaction forming 1 mole of nitrogen dioxide is 33.2 kilojoules. Let's do this. So we have 1/2 of N2 gas plus O2 gas gives us NO2 gas. Okay. So if I want to know enthalpy change for this, well, it's proportional, right? So what I've done here is I've doubled these quantities. So whatever this delta H is, this delta H equals twice it, right? So this delta H is 33.2 kilojoules per mole, right? Well, I have 2 moles of it, so this delta H is 66.4 kilojoules, right? Okay. Next thing I want you to know is that delta H for a reaction in one direction is equal to the magnitude and opposite the sign for the delta H of the other reaction. This is very, very important. Okay, so it's given us this. H2 plus Cl2 gas yields 2 HCl gas. Okay, and it's exothermic, so delta H equals negative 184.6 kilojoules. So then I'd have this question: if I went the opposite direction, I had 2 HCl and I was able to decompose it into H2 gas and Cl2 gas. First of all, if it was exothermic, it released energy to make this, then I know that this is at a lower energy state than these two were together, right? So if I want to go in reverse, it's going to be exothermic or endothermic? Endothermic. I'm going to have to put energy into the system. So I know that this sign down here is going to be positive, right? What else do I know about this sign? Or what else do I know about this number?
It means that you're adding this much energy?
Yeah, as much as I released the other
So
one,
it's the
right?
same.
So it's gonna be the same value, but opposite sign. We released energy when we went from here to here, so we'll have to put the same amount of energy in to reverse, I guess I drew it, to reverse that process, okay? Those little details of, hey, I can multiply, you know, if the number of moles of things are 2 or 3 or 4 times, then between two comparative things, then I multiply the delta H by that. Or that if I'm reversing the reaction, which you're going to have to do, then I reverse the sign. Okay? All right, well, let's do it. I actually kind of like Hess's law because it always feels like a puzzle. All right. Determine the enthalpy of formation of iron trichloride, so FeCl3. I want to find delta H for FeCl3, okay? Using the enthalpy changes of the steps leading up to it. So it gives me 2 things here. I have information you need. Fe solid plus Cl2 gas forms FeCl2, which is a solid. And the energy change associated with that is the release of 341.8 kilojoules. I also have FeCl2 solid plus 1/2 of Cl2 gas to form FeCl3 solid. So I didn't write this. And the delta H associated with that is negative 57.7 kilojoules. Okay, also exothermic. So I want to write an equation for the chemical reaction that's going to form FeCl3. I have 2 steps that are going to help me to do that. And then, of course, I need to do some work with these, right? So FeCl3 has got to be my product. Everything's got to be geared towards forming that. What's it going to be made out of? Fe, so iron. And Cl2, right? Cl2 gas to yield FeCl3. Okay. If I want to balance this, what does this need to say? I need 3 of them, right? Total. So what do I need in front of this?
3 times.
3/2. Good. So Fe solid plus 3/2 of Cl2 gas will yield 1 FeCl3 solid. Now I need to manipulate these steps to end up with this final one, okay? I'm going to erase over here so I got plenty of room to work. This is why I say I like these, they're kind of like puzzles. So I'm just going to rewrite this because I think it helps me at least to see what my goal is. Okay. personally, the way I do this, I like to start with this. I need this on the product side, right? FeCl3, we have that over here. So I'm going to take this, and it has it in the right number that I want, so I'm just going to literally write that out. You guys call it out to me, what I have, FeCl2, solid, plus 1/2 of Cl2 gas yields FeCl3. Okay. Now, I do not have FeCl2 in my products because I don't have it anywhere, right? And over here I've got my reactants. So if it's in my reactants on this one, I need it in my products on the other one, right? So if it's not already in my products, then I would need to reverse it. Just so happens it is in my products, right? So let me write it over here. FeCl2, I have 1, I have 1. This one's going to work out clean, isn't it? I didn't need to do all this. It actually just worked out. But so be it. So then I have the other side of that is Fe solid plus Cl2. It's a gas, right? When I add these up, remember that this and this will cancel because they're on opposite sides of the sign. And so I'm left with Fe solid plus 3/2 of a Cl2 gas gives me FeCl3. I didn't have to reverse a sign. I didn't have to multiply anything. And so I can literally just add these two things up. Over here, the delta H was kind of room. It was negative 341.8. It was negative 57.7. And you guys have calculators, so if you would tell me that answer, please.
399.5.
399.5 kilojoules per mole. All right, that should be the correct answer. Let's hope so. Laying on the right problem. There we go. Okay, jump page. 399, negative 399.5. I forgot my negatives. That is correct. Okay. So it's kind of a long way to get to the right answer. But I think it will prove helpful here in just a moment. I'm going to erase this side so we can work on it. All right. So the next one. Into gas plus O2 gas leaves me with 2NO2 gas. Okay. Okay, it gives me this information. It says that into gas plus O2 gas yields 2NO gas. And the delta H for this reaction is 180.5 kilojoules. And it also told me that NO gas plus 1/2 of O2 gas yields NO2 gas, and my delta H for this one is negative 57.06 kilojoules. Okay. I want this, right? So do I need to do anything to make this happen? That's the question. Do. Good, this is going to require some multiplication, right? I need 2 NO2s over here, right? So what do I need to do to this?
Multiply by 2.
Yeah, multiply what by 2? Everything by 2, right? I mean, literally the whole thing gets multiplied by 2. Need 2 of these, so I've got to multiply the whole thing by 2. When I rewrite this right here, let's say 2 NO gas plus O2 gas yields 2 NO2 gas. And my delta H is 2 times whatever this is, right? So what, negative 104.12 kilojoules?
Yes, 114.
Oh, thank you. Thank you. 114.12 kilojoules. Okay, good. Now, let's figure out what we got to do to balance this. We just dealt with this one, right? So now I got to deal with this one. My O2s are on this side on both of them. I need to get my O2s over here. So at the very least, I know that I've got to flip this whole thing, and when I do, I'm going to flip this sign too, right?
Do you need to flip it?
Maybe I don't. No, I don't. Just kidding. Maybe it's going to work out just fine. It'll be right below here. Into gas plus O2 gas yields 2 NO. Right, my NOs will cancel. So when I rewrite this formula, I'll be left with N2 gas plus 2 O2 gas yields 2 NO2 gas. Is that what I want? It is, right? So I've got this value, and my other one is 180.5 kilojoules, right? Let me just double check that my signs are all correct. That's correct. Okay, so add these up. What's our answer?
294.62.
That's not right.
Oh, it's positive on it?
So this is positive on the bottom, negative on the top.
$66.38.
Okay, let's double check that. Well, that's correct. Good, rounds up to 66.4. Okay, good. Let's go to the next one. It's funny how I thought we'd get out early, and I don't think we're getting out early. In my head, this is like, oh, we're just going to breeze through this. That's all right. At least I'm not wasting time. Chlorine monofluoride can react with fluorine to form chlorine tetrafluoride. So here's our reaction. It's Cl. Working well. ClF plus F2, these are both gases, produces ClF3. And what we're trying to do is find the delta H for this. Okay? So I'm given some information here. I'm given 3 steps. I'm told that 2OF2 gas will decompose into oxygen gas and fluorine gas, and that the energy change associated with that is the liberation of negative 49.4 kilojoules of energy. Okay. I'm also told that if I have 2 ClF gas, and I combine it with O2 gas, I will produce Cl2O gas plus OF2 gas, and the interchange associated with that is the consumption of 214.0 kilojoules of energy. And I'm given a third one, which says ClF3 gas plus O2 gas will yield 1/2 Cl2O gas plus 3/2 of OF2 gas. The energy change associated with this is consumption of 236.2 kilojoules of energy. Okay. What I need to do is I need to arrange these in such a way that the summation of them comes out to this, right? So I always like to look at my products first. I need ClF3. Where do I find ClF3?
The last one.
Where at? Here, right? Okay. So over here it's in the reactants, over here it's in the products, so I've got to reverse it. When I reverse it, I also have to reverse the sign, right? So I'm going to rewrite that whole thing. I'm going to say 1/2 of Cl2O gas plus 3/2 of OF2 gas, right? And my delta H is what?
Negative 236.2.
Negative 236.2 kilojoules. Okay, so this puts, oh, I didn't finish writing the equation, did I? Sorry about that. Let me finish this. Okay. ClF3 gas plus O2 gas, and you told me that my delta H equals negative 236.2 kilojoules. Okay. All right, that puts this on the side that I need it on. Okay. Now I need ClF and F2 to be on the reactant side. I've got an F2 here. Do I have any other F2s anywhere? No. I've got a ClF. I got a ClF here. Right? So, okay. This is 2 F2s. So I need, what do I need to do? What do I need to do with this over here?
Invert.
I need to invert it. What else do I need to do?
Divided by 2.
I need to divide it by 2. I need to take the whole thing, multiply it by a negative 1/2 kind of an idea, right? So when I do that, I'm going to have half an O2 plus F2, right? It's going to yield OF2 gas plus, oh no, that's it, OF2 gas, right? And I'm going to cut that in half and reverse the sign, so the delta H is going to be positive, and its value is going to be
Just 49.4.
49.4. I got to cut it in half.
Oh, no.
24.7.
24.7. Okay. All right. That what did that do for me? Gave me my F2 on the proper side, right? So now I come down to this one. Is this my last one? Okay. So I'm looking for, I have two CLFs, right? I'm gonna need one. So I know I've got to cut it in half. I need CLFs on the reactant side. They are on the reactant side. So for this one, all I have to do is divide the whole thing by 2, right? So when I do that, I would get CLF gas plus 1/2 of an O2 gas will give me 1/2 of a Cl2O gas plus 1/2 an OF2 gas. This is feeling very weird. And it works out, doesn't it? It's going to give me the 3/2, which I need. I was worried for a second. I'm about to look like such a moron in a second when I do this. Okay. And my delta H here is 1/2 of 214, which should be 107.0 kilojoules, right? Okay. So let's do the summation of all of this here in a second. What's on both? Well, first of all, let's highlight the things I'm really looking for. I'm looking for F2s. I'm looking for CLF gas. And I'm looking for everything else to cancel out, right? So let's start striking things. 3/2 of OF2. Here's 2/2. Something's wrong.
Because you didn't put a 1/2.
Yeah, where's it go here?
Yeah.
Okay, thank you. Okay. Here's 2/2, here's 3/2, so these get crossed out. Okay. What else needs crossing out? This gets crossed out. And oxygen gas, I got 2 of them over here. 2/2 over here is 1 hole. I got 1 hole over here. That gets crossed out. Is that everything? So when what's going on with this OF2? Oh, I forgot to cross it out, right? Is that right?
Yeah.
Okay. Okay. So when I do all this, then I get CLF gas plus F2 gas yields CLF3 gas, and my delta H equals the summation of all this. Will you guys add those up for me?
104.5 negative.
Did I do something wrong here? Should be positive, right?
Yeah.
Just double check what we got here. Yeah, well, no, you're right, it should be negative. Negative 104.5 kilojoules. Is this supposed to be negative? Did I flip something and forget to change the sign?
That's right.
Well, how could? Oh, that's 24. I had it as 247. Okay. Bless my soul. All right. I'm I'm ready to go home. Okay, do I have time? I need to have time. This is our last one. I got just enough time. Okay. There's another way to do this, same thing. I wish they'd give me more problems than this actually, because this is kind of important stuff. There is another way to do this. It's like a long way to do it, so to speak. Okay. Gotta go quick, gotta go quick. We can use Hess's law to determine the enthalpy change of any reaction if the corresponding enthalpies of formation of reactions and products are available. The stepwise reactions we consider are decomposition of the reactants into their components, elements. I'm not going to finish this. I'm not going to finish this. There's no way. This takes too much time. All right. We will have one last, that's all right, we probably need time to talk. We'll have one last problem of this next class, and then we'll start the next unit. Next class is going to be, let's look at a calendar here. Next, let's see, it's Monday, so it'll be the 23rd. Okay. Do you want to test on a Monday or a Wednesday? On Wednesday? Okay. So then November 4th, unless you want it the day after we finish the unit. So we won't do that. So your test will be November 4th.
Or it's Monday.
I went the wrong way in my calendar. Okay, let's try this again. What is today?
Today's 21,
Today's the 21.
Wednesday's
I'll
20.
finish on Wednesday. Do you want your test on the 30th or the 6th? Do you want more time to study? Or are you worried about, hey, that'll be so far away since I used it? Those are things you
I
balance.
prefer more time.
Okay, November 6th, that is our test, okay? All right, that gives you plenty of time. I will get you homework, Lord willing, next class. All right, y'all have a great day, okay?